Gravity is the one cosmic force that stubbornly refuses to play by the quantum rules. All the other forces of nature have been successfully described by quantum mechanics, but gravity remains the ultimate outsider. This single inconsistency points to a deeper, hidden layer of reality, and to find it, we must venture into the wild world of quantum gravity. In this journey, we will explore 30 of the most incredible theories physicists have devised to solve this puzzle. By the end, you will understand the leading contenders in the race to unify all of physics. We will see how some theories suggest our universe is a hologram, while others propose that space and time are made of tiny, vibrating loops. What idea do you think could finally crack the code of our cosmos? The first great candidate to unite these worlds proposes that the very idea of a point-like particle is an illusion. At the heart of string theory lies a beautiful and radical idea. What if the fundamental building blocks of the universe are not zero-dimensional dots, but incredibly tiny, vibrating loops of energy? Think of the strings on a violin. A single string can vibrate in many different ways, producing a unique note from a low C to a high A. In string theory, these tiny cosmic strings work in a similar way. Each distinct pattern of vibration corresponds to a different type of particle. One specific vibration might create an electron, another a quark, and remarkably, one special vibration would produce the graviton, the hypothetical particle that carries the force of gravity itself. This single, elegant framework promises to explain every force and every speck of matter in the cosmos, all from the music of these tiny strings. It is a symphony of creation written into the fabric of reality. But for this beautiful music to be mathematically consistent, the strings cannot simply vibrate in the 3 dimensions of space and 1 of time that we experience. They require extra dimensions curled up into shapes so small we never notice them. This is the astonishing price of unity, a universe with hidden, folded spaces existing at every single point. While string theory weaves gravity into a cosmic symphony with extra dimensions, a radically different challenger approaches the problem from the opposite direction. Loop quantum gravity makes no attempt to replace the point-like particle. Instead, it asks a more fundamental question. What if space and time themselves are not smooth and continuous, but are actually made of discrete, individual bits? Imagine looking at a digital photograph on a screen. From a distance, the image appears seamless and fluid. But if you zoom in far enough, you eventually see the individual pixels, the tiny squares of color that compose the entire picture. Loop quantum gravity proposes that our reality works in the same way. The seemingly smooth emptiness of space is not empty at all. It is woven from an unimaginably dense fabric of tiny, one-dimensional loops. These loops connect with one another, forming a dynamic web often called a spin network. This is the quantum code of spacetime. In this framework, you cannot have a volume of space that is arbitrarily small. There is a smallest possible volume, a fundamental pixel of reality. The same applies to time. Time may not flow like a river, but could instead tick forward in the tiniest, discrete steps, like the second hand on a cosmic clock, advancing 1 Planck time at a time. This granular structure provides a natural limit to the universe, preventing the infinite densities that create black hole singularities and the Big Bang. What makes this theory so compelling to many is its core principle of background independence. It does not describe particles moving on a fixed stage of spacetime. Instead, the loops and their connections are the stage. Space and time emerge from the relationships between these fundamental quanta. This is a universe where geometry is not a backdrop, but a dynamic, evolving entity. So, do we live in a universe of vibrating strings in hidden dimensions, or is our reality a vast, evolving spin network of quantum space? But what if the fabric of spacetime is not a smooth sheet or a spin network, but something built from simple, geometric pieces? Causal Dynamical Triangulations offers a radically different picture, modeling the universe as a vast cosmic Lego set. In this approach, the fundamental building blocks are not loops or strings, but tiny, four-dimensional triangular shapes called simplices. Think of them as the pixels of spacetime, but with a crucial, built-in rule. Each of these geometric pieces is connected to its neighbors in a way that strictly respects cause and effect. This causal rule is the theory's master architect, preventing the spacetime foam from becoming a chaotic mess. Without this guiding principle, the quantum building blocks would connect in every possible way, instantly spawning a wild proliferation of disconnected baby universes and bizarre pathological shapes. Our orderly cosmos would never form, but by insisting that time must always flow forward in a well-defined sequence, the theory tames the quantum chaos. It allows the simple blocks to assemble themselves into a structure that, when you zoom out to our human scale, looks exactly like the smooth, four-dimensional universe we recognize. The emergence of a familiar reality from such simple ingredients is a profound result. It suggests that the flow of time and the vastness of space are not fundamental, but collective phenomena, much like the smoothness of a sheet of paper emerging from the tangled fibers of wood pulp. So we have strings, loops, and now geometric blocks. Is our universe a consequence of its own causal architecture, a stable structure that won the cosmic lottery against infinite chaos? A fourth path to quantum gravity presents an elegant alternative to adding new dimensions or pixels. This is the idea of asymptotic safety. Imagine a river flowing towards a waterfall. As the water approaches the edge, its speed and energy seem to increase without limit, heading for a catastrophic plunge into infinity. For decades, physicists thought this was the inevitable fate of quantum gravity at the highest energies. The equations predicted that the force would become infinitely strong, making any calculation meaningless. But what if the river, just before the brink, found a stable plateau? A place where the water could swirl in a perfect, self-regulating eddy, never actually falling over the edge. Asymptotic safety proposes that gravity does exactly this. It suggests that gravity is, in fact, a perfectly sensible quantum theory all on its own, without needing strings or loops, provided it possesses one special property. At incredibly high energies, like those present at the birth of the universe, the strength of the gravitational force must reach a fixed finite value. It becomes safe rather than blowing up to infinity. This fixed point acts like a cosmic anchor, taming the wild quantum fluctuations that would otherwise tear spacetime apart. In this view, gravity is not a problem to be solved by reinventing reality. It is a complete and consistent theory whose key has been hidden in plain sight all along, waiting for us to learn how to turn the lock. The universe's most stubborn force may not need a revolution, but a deeper understanding of its own inherent, self-controlling nature. So is gravity's quantum secret not a new structure, but a hidden stability written into the very laws of physics. Yet another theory turns our entire understanding of gravity on its head. What if gravity is not a fundamental force of nature at all, but something that simply emerges from a deeper, more basic layer of reality? This is the radical proposal of emergent gravity. Think about the concept of temperature. If you touch a hot stove, you feel heat, but what is heat really? At its core, it is not a fundamental entity. It is an emergent property that arises from the frantic, collective jiggling of countless atoms and molecules. The heat you feel is just the average kinetic energy of those invisible particles. Emergent gravity suggests that the force which holds planets in orbit and pulls us to the ground is just like that heat. It is not a primary ingredient of the universe, but a side effect, a statistical mirage that appears when we look at the world from our large human scale. The true fundamental reality might be built from something entirely different, a vast network of quantum information and entanglement. In this view, spacetime itself is not the starting point. It is a kind of illusion, a hologram that projects from a lower dimensional system where quantum bits are intricately woven together through entanglement. The force we call gravity would then emerge from the way this quantum information is organized and connected, much like the pressure in a gas emerges from countless molecular collisions. This idea dramatically reinterprets Einstein's general relativity. His beautiful description of gravity as the curvature of spacetime would not be wrong, but it would be like the elegant equations of thermodynamics. They perfectly describe the behavior of steam engines and ice cubes without ever needing to mention a single atom. So is the cosmos we perceive just the visible tip of a hidden, information-based iceberg, with gravity as its most profound and convincing illusion. Our reality might be nothing more than a magnificent projection. This is the startling claim of the holographic principle, a theory that redefines the very nature of information and space. Imagine a credit card hologram, a flat, two-dimensional surface that encodes a stunningly realistic three-dimensional image. The holographic principle suggests our universe operates in a surprisingly similar way. It proposes that all the information needed to describe everything within a certain volume of space, every star, every planet, every person, is actually encoded on the two-dimensional boundary that surrounds it. In this view, the three-dimensional world we see and touch is not the fundamental reality. It is a holographic projection from that distant, flat surface. The implications are staggering. Your perception of living in a rich, three-dimensional world could be an elaborate illusion, a cosmic mirage generated from a vast, thin shell of quantum data. This idea finds a powerful anchor in the study of black holes. A black hole's event horizon is its ultimate point of no return, a two-dimensional surface from which nothing, not even light, can escape. Physicists discovered that the maximum amount of information a black hole can contain is not proportional to its volume, but to the surface area of its event horizon. This was the first concrete hint that information in our universe might prefer to live on surfaces, not within volumes. The holographic principle takes this black hole revelation and applies it to the entire cosmos. It forges a profound and unexpected link between gravity and quantum mechanics, suggesting that gravity itself emerges from the quantum information stored on the universe's outer shell. So, the force that shapes the cosmos on its grandest scales may be a direct consequence of how data is painted onto the universe's ultimate canvas. Are we, and everything we know, just a ghostly image cast from the edge of reality? Two more profound theories offer a completely new mathematical language for describing the fabric of reality. Causal set theory proposes a universe of breathtaking simplicity. What if the entire cosmos, from the Big Bang to this very moment, is just a vast collection of discrete events like grains of sand? These individual events are the fundamental atoms of space-time. They are not placed within a pre-existing arena of time and space. Instead, the only thing that defines them is their relationship to one another, a simple before and after. A single, fundamental relation of causality connects them, stating that one event can influence another. From this sparse, minimalist network of cause and effect, the entire four-dimensional universe of space and time is born. The smooth, continuous geometry we perceive is just a secondary, large-scale illusion. Much like the smooth curve of a beach emerges from countless individual grains when viewed from a distance. The very dimensionality of our world, the fact that we experience exactly three dimensions of space and one of time, might be a consequence of how these causal links are woven together. In this view, reality is not a stage where events play out. It is the sequence of events themselves. Then we have non-commutative geometry, a theory that rewrites the rules of measurement at the universe's smallest scales. In our everyday world, the order in which you do things does not always matter. You can walk 5 steps north and then 3 steps east, and you will end up in the exact same spot as if you had walked 3 steps east first and then 5 steps north. Your coordinates commute, but in the quantum realm, this common-sense rule breaks down. Non-commutative geometry proposes that at the Planck scale, the very concept of a precise location dissolves. It is impossible to simultaneously measure position and movement with infinite accuracy. The order of your measurements now matters profoundly. This fundamental fuzziness means that spacetime itself becomes a blurry quantum foam. It is no longer a smooth manifold where you can pinpoint an event, but a seething, uncertain landscape where the very ideas of here and there lose their absolute meaning. This theory replaces the classical, continuous geometry of points with an abstract algebra of relationships, suggesting that the quantum nature of reality is written not in the language of shapes, but in the non-commutation of its fundamental operations. So, is our universe built from a cosmic chain of causes, or is it a realm where geometry itself becomes an uncertain quantum whisper? The elegance of symmetry could be the secret weapon in the long battle to unite gravity with the quantum world. Supergravity is a theory that marries the profound insights of Einstein's general relativity with a powerful concept known as supersymmetry. This idea proposes a deep and beautiful kinship between the two fundamental classes of particles in the universe, the fermions that build matter and the bosons that carry forces. Supersymmetry suggests that for every known particle, there exists a hidden, super-heavy superpartner. For every quark, there would be a squark, for every electron, a selectron. And for the force-carrying particles, the photon would be paired with a photino and the graviton with a gravitino. This cosmic doubling is not just for show. The introduction of these superpartners creates a perfect mathematical balance that smooths out the violent quantum fluctuations which normally cause gravity's equations to explode into infinities. It is like adding a counterweight to an unstable system, bringing everything into a harmonious equilibrium. In supergravity, this symmetry is applied directly to the fabric of spacetime itself, suggesting that the very geometry of the cosmos is supersymmetric. The theory paints a picture where the force of gravity is not a brute, singular entity, but is gracefully intertwined with a family of related superpartners, all working in concert to shape a stable and coherent universe. This elegant framework was a crucial stepping stone, demonstrating that a quantum theory of gravity could be mathematically consistent and paving the way for its more famous descendant, superstring theory. Yet the superpartners it predicts remain stubbornly hidden from our most powerful particle colliders, leaving us to wonder if this beautiful symmetry is a true feature of nature or a magnificent mathematical mirage. A universe built from points in space may be a flawed starting point. Roger Penrose's twistor theory offers a profound shift in perspective. It suggests that the fundamental objects of reality are not points at all, but something even more basic called twistors. Imagine trying to describe a ray of light. In our usual way of thinking, we would plot its path through space and time, marking its position at each moment. But a twistor captures the entire history of that light ray in one single, elegant geometric object. It is not a point in space, but a representation of a light ray's complete journey. In this framework, spacetime itself, with all its points and events, is not the primary reality. Instead, space and time emerge from a vast, interconnected network of these twistors. It is as if we have been trying to understand a painting by only analyzing the individual dots of pigment, while twistor theory asks us to step back and see the brushstrokes that define the entire image. This radical reformulation provides a completely new mathematical language for physics. The notoriously difficult equations of quantum gravity can become dramatically simpler and more natural when written in the language of twistors. The theory hints at a deep and unexpected union between quantum mechanics and the large-scale structure of the cosmos, all by replacing the idea of where something is with the more fundamental concept of how things are related through light. Could the key to quantum gravity lie not in the fabric of space, but in the timeless paths of light from which space is woven? These abstract spin networks of loop quantum gravity require a deeper dynamic principle to truly come alive. Group field theory provides that missing engine of creation. It proposes that the fundamental ingredients of reality are not the loops or the nodes themselves, but even more basic quantum grains akin to abstract atoms of space. Picture a calm, clear glass of water. The water appears as a single, continuous, transparent substance, but we know this is an illusion. The water is actually a collection of countless H2O molecules, each jostling and interacting with its neighbors. The smooth, fluid behavior we see is a collective phenomenon emerging from the collective dance of all these individual parts. Group field theory suggests that spacetime itself is like that water. The seemingly smooth, continuous stage of our universe is actually a condensate, a collective state of an unimaginable number of these fundamental quantum building blocks. In this framework, the familiar geometry of space and the flow of time are not fundamental. They are illusions that appear when these abstract quanta lock into a shared, coherent state, much like individual water molecules coalescing to form a flowing liquid. The theory's mathematical machinery describes how these quanta interact, bond, and organize themselves. A single interaction between these building blocks might create a single loop of the spin network. More complex interactions weave these loops into the full, dynamic fabric of spacetime, so the galaxies, planets, and the space between them are not placed within a container. They are the visible manifestation of a cosmic condensate, a frozen structure born from the frenetic interactions of reality's most basic ingredients. Is the universe not a place, but a thing, a physical substance that congealed from a more primitive state of existence? Time itself may be the one absolute ruler in the cosmos. Shape dynamics challenges our most basic assumptions by proposing that while the flow of time is fundamental, the size of things is not. In our everyday experience and in Einstein's general relativity, the scale of objects seems absolute. A meter is a meter everywhere and always, but this theory suggests that this is an illusion. What if the universe has no preferred scale? What if the concept of absolute size simply does not exist? The only thing that is physically real is the shape of the universe, the angles and proportions between objects, and the sequence of how that shape changes in time. Imagine an expanding universe like a balloon being inflated. From our perspective, galaxies are flying apart. But in the view of shape dynamics, you could just as accurately describe the same situation as the universe staying the same size while all the matter within it is shrinking. There is no experiment you could perform from inside this cosmos to tell the difference, because all your measuring rods would be shrinking too. The physics depends only on the relational shapes, not on an absolute yardstick. This perspective offers a radical solution to the infamous problem of time in quantum gravity. Other theories often struggle to define what time actually is at the most fundamental level, sometimes suggesting it emerges from a timeless quantum soup. But shape dynamics boldly reinstates time as the primary, flowing reality. The universe is a movie, not a photograph. It is a story about the evolution of pure shape, a cosmic ballet where the dancers and the stage are constantly redefining their size in a grand, scale-free harmony. Could it be that the relentless tick of time is the only true constant, and the vast emptiness of space is merely its relative and illusory canvas? What if the force that binds the cosmos is not a force at all, but a kind of cosmic forgetfulness? This is the startling premise of entropic gravity. Eric Verland proposed a theory so radical it reframes gravity not as a fundamental interaction, but as a side effect of disorder. Think of a child's room. When toys are scattered everywhere, the room is in a state of high entropy, a state of high disorder. It takes energy and effort to tidy them up, to create a state of low entropy and high order. Now imagine the entire universe is filled with an invisible, fundamental substance, a kind of cosmic substrate. When you place an object like a planet into this substrate, it pushes the substrate's components aside, creating a region of lower entropy, a more ordered state around it. The universe, tending toward maximum disorder, resists this. It responds by effectively pushing back, creating a force that seems to pull other objects toward the first one. This push, driven by the natural tendency toward disorder, is what we perceive as gravity. It is an entropic force emerging from the statistical drive toward chaos, much like the pressure in a gas emerges from countless random collisions. Verlaine did not just offer this as a poetic idea. He showed that this thermodynamic reasoning could mathematically derive Newton's law of universal gravitation, the very equation that has described the pull between stars and planets for centuries. The force we have attributed to the curvature of spacetime might simply be nature's way of maximizing its own disorder, a cosmic shrug against our attempts to impose order. Is gravity, then, the universe's most profound and persistent memory lapse, a collective amnesia that gives rise to the illusion of attraction? 14 theories in, and we arrive at a framework that refuses to give up on the old ways. Quantum Einstein gravity takes the tools that worked for every other force and asks a daring question. What if we can quantize gravity after all, just by being smarter about how we use them? This approach relies on a powerful technique called the functional renormalization group. It is a method for understanding how a theory evolves, not over time, but across different scales of energy. Imagine you are using a microscope to examine a piece of fabric. With a low-power lens, the material looks smooth and continuous. As you turn the dial to a higher magnification, you begin to see the individual threads. Zoom in further, and you see the tiny fibers that make up each thread. The functional renormalization group provides the mathematical equivalent of that microscope dial. It allows physicists to track how the strength of the gravitational force changes as we probe smaller and smaller distances, approaching the violent energies of the Big Bang. For decades, the conventional wisdom was that this zoom would reveal a disaster. Gravity would appear to grow infinitely strong, and the equations would become useless, a problem known as non-renormalizability. But quantum Einstein gravity, through intricate calculations, suggests a different outcome. It finds evidence for a cosmic attractor, a fixed point where the force's strength stabilizes. This is the very essence of asymptotic safety in action. At the highest energies, gravity does not run wild. It settles into a perfectly well-behaved, self-regulating state. In this view, Einstein's original theory of general relativity is not wrong. It is simply the low-energy, large-scale face of a complete and consistent quantum theory. The equations we have trusted for a century are just one piece of a much larger puzzle, valid for describing planets and galaxies, while the full quantum theory takes over in the realm of the ultra-small. This framework paints a compelling picture of unity, suggesting that gravity may finally be tamed not by reinventing reality, but by deepening our understanding of the field theory we already have. What if the speed of light is not the universe's ultimate speed limit, but merely a local ordinance? Horava-Lifshitz gravity proposes a radical division in the laws of physics, suggesting that time and space are not the unified partners Einstein described. At the high-energy, frenetic pace of the quantum realm, this theory dares to break a sacred principle known as Lorentz invariance, the idea that the laws of physics look the same for all observers moving at constant speed. By treating time fundamentally differently from space, the theory gives gravity a new set of rules at tiny scales. Imagine a world where a film projector suddenly malfunctions. The images on the screen, which once flowed smoothly together, now stutter and jump, with time advancing in a distinct, separate rhythm from the unfolding of the spatial scene. Horava-Lifshitz gravity suggests that spacetime itself behaves similarly at its most fundamental level. This separation has a powerful payoff. It tames the wild infinities that have plagued every previous attempt to quantize gravity using standard field theory methods. The mathematical adjustments required to treat time separately make the theory renormalizable, meaning physicists can finally get sensible, finite answers out of their calculations even at the highest energies. It is a pragmatic solution that sacrifices a cherished symmetry for the prize of a workable theory. Yet the cost is profound. It challenges a core tenet of relativity that has been experimentally verified time and again in our low-energy world. So we are left with a compelling dilemma. Is Lorentz invariance a truly fundamental feature of the cosmos, or is it just an emergent, low-energy illusion? A peace treaty that holds in our quiet corner of the universe but is shattered in the violent cradle of creation. Some theories suggest that space is a secondary structure, but where could it possibly emerge from? Matrix models offer one of the most concrete answers, proposing that the entire universe might be built from nothing more than simple grids of numbers. Imagine a vast spreadsheet where each cell contains a number that can interact and evolve according to specific mathematical rules. In this framework, these matrices are not sitting in space. They are the precursors to space itself. This approach provides a complete, non-perturbative formulation of string theory, but with a fascinating caveat. It works most naturally for a universe that has only one dimension of time and one dimension of space. From the interactions of these abstract numerical grids, the familiar vibrations of strings, and even the dimension of space they move in can spontaneously materialize. It is a vision of creation where geometry is born from algebra, yet our world has three spatial dimensions, not one. This is where tensor models enter the picture. Think of a tensor as a multi-dimensional spreadsheet, a mathematical object that can be thought of as a cube or a hypercube of numbers rather than a simple flat grid. Tensor models are the natural, more powerful generalization of matrix models designed to construct higher dimensional spaces. They provide the dynamic engine for the quantum grains in group field theory. Each interaction between the components of these vast, abstract tensors can be seen as gluing together the fundamental atoms of space, building up the spin networks that weave together our cosmic fabric. In this breathtaking picture, the three-dimensional volume of the room you are in and the space between galaxies is a grand structure assembled from the collective behavior of these primordial quantum data blocks. The universe may not be written in the language of physics, but in the silent, ceaseless computation of mathematics. Could everything we see and feel be the output of a cosmic calculation happening in a realm before space and time even existed? The spin networks of loop quantum gravity describe space at a single frozen moment, but how does this cosmic fabric actually change and evolve? For that, we need to look deeper into the dynamic history of spacetime itself. This is the realm of spin foam models. If a spin network is a single, still frame of the universe, then a spin foam is the entire movie. It represents the entire history of spacetime, not as a smooth continuum, but as a complex, foaming structure where the spin networks themselves evolve, merge, and split. The name is a perfect description. Picture the effervescent foam on the surface of a freshly poured drink. Each delicate bubble is constantly shifting, merging with its neighbors or splitting apart to form new ones. A spin foam is a quantum version of this, a foaming sea of change where the bubbles are the elementary units of spacetime, constantly interacting and transforming. Each slice through this foam is a spin network, a snapshot of space at one instant. Stack these slices together and you get the full, four-dimensional history of the cosmos. This formalism provides a path-integral approach to quantum gravity. Instead of asking for one specific history of the universe, it considers every single possible way that spacetime could have evolved from an initial state to a final one. It sums over all these possible histories, each one a different, intricate spin foam. In this grand quantum calculation, even the most bizarre and unexpected transitions have a tiny probability of occurring. A single loop of space might wink out of existence, or two might combine to form a new one. The entire geometry of the universe is in a constant, shimmering dance of creation and annihilation at the Planck scale. The smooth, predictable evolution of spacetime we experience is just the average classical outcome of this unimaginably vast and frenetic quantum ballet. So the fabric of reality is not a static tapestry, but a living, breathing, and foaming entity, with every possible past simultaneously contributing to the present we perceive. A universe built from matter is the bold starting point of our next theory. Causal Fermion systems proposes a framework so comprehensive it begins not with space, not with time, but with the most fundamental stuff we know, the fermions that constitute matter itself. In this view, electrons, quarks, and neutrinos are not inhabitants of spacetime. They are the architects of it. The theory introduces a new fundamental object, the causal fermion, which represents the physical state of all matter fields at a point. But here is the profound shift. These points are not points in a pre-existing space. They are the primary entities, and the only structure that defines them is a single fundamental relation, causality. Each causal fermion carries a label that determines whether it can influence another or be influenced by it. From this sparse, minimalist network of cause and effect, the entire tapestry of spacetime, along with its geometry and even the other forces of nature, is woven into existence. The stage emerges from the actors, the gravitational field, the electromagnetic field. Everything we observe is a secondary manifestation of the dynamics and interactions between these fundamental matter units. It is a complete reversal of the traditional picture, offering a unified description of gravity and the quantum world by asserting that matter does not simply live in the universe. Matter, through its causal relationships, actively constructs the universe around it. Could the cosmos be a grand, evolving network of cause and effect, with the particles of matter themselves laying down the very rails of time and space upon which they travel? The universe might have no beginning and no end, not in time, but in a more profound, static sense. This is the strange world unveiled by the Wheeler-DeWitt equation, a monumental attempt in the 1960s to treat the entire cosmos as a single quantum object. John Wheeler and Bryce DeWitt applied the rigorous rules of quantum mechanics directly to Einstein's description of gravity. The result was an equation for the wave function of the universe, a single mathematical object that supposedly contains the quantum description of all that ever was or could be. But this equation came with a shocking and deeply puzzling feature. The variable for time simply vanished from the mathematics. The Wheeler-DeWitt equation describes a universe that just is. It is a timeless blueprint of reality, a frozen snapshot where the Big Bang is not an event in the past but merely one particular configuration within an eternal, unchanging quantum state. This is the infamous problem of time in quantum cosmology. If this equation is the ultimate truth, then the flow of time, the relentless march from past to present to future, is a complete illusion. Your childhood, this very moment, and every future event would all exist simultaneously, locked in a static quantum structure. It is as if the entire history of the cosmos is a finished film, and our conscious awareness is just a spotlight moving sequentially from one frame to the next, creating the convincing but false sensation of a flowing now. How can our most fundamental experience of reality emerge from a theory that has no place for it? The Wheeler-DeWitt equation stands as a stark reminder that in our quest to unify physics, we may be forced to abandon our most basic intuitions about the nature of existence itself. A black hole's appetite is not infinite. The discovery that these cosmic monsters must obey the laws of thermodynamics forever changed our understanding of gravity. It began with a simple, profound realization. If you drop a cup of hot coffee into a black hole, you are increasing the black hole's mass, but you are also erasing the entropy, the disorder that was contained in the coffee's heat. This act would seem to violate the second law of thermodynamics, which states that the total disorder in the universe can never decrease. To resolve this paradox, Jacob Bekenstein made a radical proposal. What if a black hole itself possesses entropy, and a tremendous amount of it? He suggested that a black hole's entropy is proportional to the surface area of its event horizon. This was a staggering idea. Entropy is a measure of the number of ways a system's internal parts can be rearranged without changing its overall appearance. For a gas, this means counting all the possible positions and motions of its molecules. For a black hole, its entropy being tied to its surface area implied that all the information about everything it has ever swallowed is somehow encoded on its two-dimensional boundary. The event horizon is not a smooth, featureless wall. It must be made of an unimaginably vast number of microscopic quantum degrees of freedom, a fine-grained structure etched onto the surface of the void. This was the first concrete hint that spacetime itself has a quantum microstructure. Then Stephen Hawking took this a step further, applying quantum theory to the space just outside the event horizon. He found that the intense gravitational field can spontaneously create pairs of virtual particles. Normally, these particles would annihilate each other in an instant. But if one particle falls into the black hole while its partner escapes, the black hole loses a tiny amount of mass in the process. To an outside observer, the black hole is not completely black. It glows with a faint heat now known as Hawking radiation. This radiation carries away energy, causing the black hole to slowly shrink and eventually evaporate. The hotter a black hole is, the faster it evaporates, perfectly mirroring the behavior of any other hot body in the universe. Black hole thermodynamics was born, complete with its own set of laws. This union of gravity, quantum mechanics, and thermodynamics is one of the strongest clues we have. It tells us that gravity is not separate from the quantum world. The entropy formula, written on the horizon of a black hole, is a direct message from the quantum grains of space-time, a fundamental memo about how reality is built. Two particles separated by a vast cosmic distance can share a mysterious, instantaneous bond known as entanglement. This quantum link, famously derided by Einstein as spooky action at a distance, seems to defy the speed of light, connecting the fates of the particles no matter how far apart they fly. Yet what if this spooky connection is not a ghostly abstraction, but a physical structure woven from the fabric of spacetime itself? The ER equals EPR conjecture dares to propose exactly that. It suggests that two entangled particles are not communicating faster than light. Instead, they are intimately connected by a microscopic wormhole, an Einstein-Rosen bridge, a tiny tunnel threading through the quantum foam of spacetime. In this radical view, quantum entanglement and the geometric portals of general relativity are not two different phenomena. They are one and the same thing, described in two different languages. The spooky action is the wormhole. This idea forges a breathtaking bridge between the two greatest pillars of modern physics. Quantum mechanics with its entangled particles and general relativity with its warped spacetime geometry are revealed as two sides of a single, deeper coin. It transforms the paradox of entanglement from a philosophical puzzle into a tangible, physical architecture. The universe is not just weird, it is physically threaded together by an unimaginably complex web of these microscopic tunnels, linking every entangled particle, every quantum bit, into a single, inseparable whole. So the next time you hear about particles influencing each other across the galaxy, you can picture not an invisible signal, but a sub-microscopic shortcut through the folded heart of spacetime itself. Is the entire cosmos one vast, interconnected network of quantum threads and gravitational stitches? Geometry itself might be the ultimate foundation of reality. Tucked within the complex mathematics of particle collisions, physicists discovered a stunningly simple object called the amplituhedron. This multi-dimensional, jewel-like shape is not a physical object in space. It is a purely mathematical discovery that calculates the outcomes of particle interactions with an efficiency that seems almost magical. Normally, predicting how particles will scatter after a high-energy collision involves nightmarishly long calculations, summing over an infinite number of possible paths and intermediate steps, a process riddled with cancelling infinities. The amplituhedron sidesteps this entire mess. The probability of a specific outcome is found not by laborious summing, but simply by calculating the volume of this geometric shape. It is as if, after years of adding up every single brushstroke that could possibly make a painting, someone handed you a ruler and said, "Just measure the canvas." This discovery suggests that the tangled quantum weirdness of probabilities and virtual particles might be a shadow cast by a deeper, more perfect geometric reality. The implications for quantum gravity are profound. The amplituhedron formulation makes no direct reference to two of our most fundamental concepts: locality, the idea that particles interact at specific points in space, and unitarity, the conservation of probability. These principles are not inputs into the geometry, they are outputs that emerge from it. This hints that space and time, and even our core quantum rules, might not be fundamental ingredients of the universe. They could be secondary properties that arise from a more primary, geometric world that exists beyond space and time. The force of gravity, which is so deeply intertwined with the geometry of spacetime, might find its truest description not in dynamic equations, but in the timeless, elegant volumes of shapes like the amplituhedron. Are the laws of physics ultimately just the shadows of perfect, eternal forms? Gravity appears to be the weakest force in the universe, a fact that has always puzzled physicists. A single small magnet can lift a paperclip, effortlessly overcoming the gravitational pull of the entire Earth. But what if this incredible weakness is not a fundamental property? What if the force-carrying particle of gravity, the graviton, actually has a tiny mass? This is the provocative premise of massive gravity. In our standard understanding, the graviton is massless, just like the photon, which allows gravity to reach across the vast emptiness of space to hold galaxies together. A massless graviton means the force follows the familiar inverse square law perfectly, its influence diminishing with distance but never quite vanishing. If the graviton possesses even an infinitesimal mass, however, the equations of gravity change dramatically over cosmic scales. The force would weaken and effectively cut off after a certain immense distance. Picture a radio signal that can only travel so far before it fades into static. A massive graviton would act similarly, its influence decaying faster over intergalactic distances than we currently expect. This modification offers a tantalizing solution to one of cosmology's biggest mysteries, dark energy. The observed accelerated expansion of the universe is currently attributed to this mysterious energy permeating the vacuum of space. But massive gravity provides an alternative. The apparent push of dark energy might not be a new, exotic substance at all. It could be an illusion created by the gradual weakening of gravity's pull on the largest scales, a direct consequence of the graviton's mass. The cosmos would not be filled with a repulsive energy, but would simply be feeling the limits of its own fundamental force. This elegant idea reinterprets one mystery as a subtle feature of another, suggesting that the key to the universe's expansion has been hiding in the properties of gravity all along. Einstein's geometric masterpiece may not be the only way to describe the cosmos. A powerful alternative simply changes the geometry of the problem. Teleparallel gravity is an equivalent reformulation of general relativity, but it swaps the central actor. Instead of using the curvature of spacetime to explain gravity, it uses a property known as torsion. Think of two different ways to navigate a mountain. In Einstein's view, a heavy object like the Sun creates a deep valley in the fabric of spacetime. The Earth moves along this curved landscape, following the downhill slope, which we perceive as gravitational attraction. Teleparallel gravity offers a different path. Imagine the same mountain, but now it is covered with a perfectly level, grid-like network of roads. The sun does not create a valley. Instead, it introduces a twist, a torsion, into this grid. The roads themselves remain flat and straight, but they are now slightly screwed up relative to each other. An object moving along these twisted roads will still find itself veering towards the sun, not because it is rolling downhill, but because the very definition of a straight line has been subtly rotated around it. The gravitational pull feels the same, but the underlying mechanism is completely different. This shift in perspective offers a profound potential advantage. The mathematics of curvature in general relativity are notoriously difficult to marry with quantum principles, but torsion behaves much more like the other fundamental forces, such as electromagnetism. These forces are described by a powerful mathematical framework known as gauge theories. In teleparallel gravity, gravity itself can be reinterpreted as a gauge theory for translations in space. This reframing makes it look and act much more like its quantum cousins, potentially smoothing the path to a full theory of quantum gravity. It is as if we have been trying to fit a square peg into a round hole for a century, and this theory suggests we simply turn the peg sideways, revealing a shape that slides perfectly into place. Could the key to unification have been hiding in a different kind of geometric twist all along? Spacetime may be the grandest illusion of all. The theory of pregeometry dares to suggest that the stage itself is not fundamental. The three dimensions of space and the relentless flow of time are not the starting points of reality. They are a consequence, a collective behavior that emerges from a deeper, more primitive layer of existence. This foundational layer is not made of stuff in the traditional sense. It is often conceived as a vast, seething network of quantum information, or a web of pure, abstract relationships where concepts like here and there have no meaning yet. Imagine the bustling activity of a city. From high above, you see streets, traffic flows, and distinct neighborhoods. This emergent structure is space-time. But if you could descend to the absolute ground level, you would not find a paved road or a building foundation. You would find only the countless individual decisions and interactions of people, each one following their own local rules. The city's geography is not a pre-drawn map they walk on. It is a dynamic pattern that crystallizes from their collective behavior. Pregeometry proposes that the cosmos works in the same way. The smooth, continuous geometry of general relativity is the city seen from the sky. The quantum informational network, the pre-geometric substrate, is the ceaseless activity of its citizens. In this view, an electron does not move through space. The very notion of its position is defined by its relationships to every other bit in the network. The gravitational field is not a curvature of a pre-existing stage. It is a manifestation of how the information in the network is entangled and connected. This idea pushes our understanding to its absolute limit, forcing us to question if the universe requires any container at all, or if the container is simply the most stable pattern that the underlying quantum data can form. Are we and the space we inhabit just a temporary consensus in an ocean of primordial possibility? Every force in the universe seems to have a quantum shadow, a faint energy humming in the void. According to our best quantum theories, empty space is not empty at all. It is a seething, bubbling foam where virtual particles flicker in and out of existence in a relentless quantum dance. Every cubic centimeter of this vacuum should possess a staggering amount of energy, a pressure inherent to space itself. This is the cosmological constant, and its predicted value creates the most shocking mismatch in all of physics. When we calculate how much this vacuum energy should curve spacetime, the result is a number so immense it is laughable. It suggests a universe that should have ripped itself to shreds in a violent, exponential expansion within the first fraction of a second of the Big Bang. Yet when we look through our telescopes, we measure the actual expansion rate. the observed value of the cosmological constant is not just a little smaller than the prediction. It is 120 orders of magnitude smaller. That is a 1 followed by 120 zeros. This is not merely a rounding error. It is the most precise and embarrassing failure of theoretical physics, a screaming void between prediction and reality. The cosmological constant problem is not a theory of quantum gravity, but a brutal judge. Any theory that claims to unite quantum mechanics and gravity must, as its first and greatest test, explain this monstrous discrepancy. It must tell us why the vacuum energy, which should be immense, is almost exactly zero. Is there a hidden symmetry that perfectly cancels it out, a cosmic fine-tuning of unimaginable precision? Or does it mean our understanding of the quantum vacuum is fundamentally wrong? Perhaps gravity does not respond to vacuum energy in the way we think. Maybe the universe possesses a memory, a kind of cosmic inertia that prevents it from feeling the full quantum fury of empty space. Solving this puzzle is the ultimate gatekeeper. The answer will not just correct a number, it will reveal how deeply intertwined the quantum world and the structure of spacetime truly are. The holographic principle finds its most precise mathematical expression in a breathtaking correspondence. Conformal field theories are special quantum systems that look the same at every scale, possessing a perfect symmetry under stretching and scaling. Imagine a pattern on a rug that remains perfectly unchanged no matter how much you magnify it. These CFTs are proposed to live on the lower dimensional boundary of a universe. The stunning revelation of the AD-SCFT correspondence is that this quantum theory on the boundary is completely equivalent to a theory of gravity operating in the full, higher dimensional interior of an anti-de Sitter space. Anti-de Sitter space is a universe with a peculiar geometry, one whose empty space naturally curves inward with a constant negative curvature, creating a kind of gravitational basin. In this cosmic dictionary, every single entry on one side has a perfect translation on the other. A complex calculation involving the collision of gravitons in the warped interior of the space is exactly mirrored by a much simpler calculation involving the quantum entanglement of particles on the flat boundary. The force of gravity and the very dimension of space emerge from this duality. This makes the correspondence one of the most powerful tools ever discovered for tackling quantum gravity. Physicists can now study the notoriously difficult problems of black holes and quantum spacetime by performing much more manageable calculations in the well-understood language of quantum field theory on the boundary. It is like trying to understand the intricate physics of a stormy ocean by instead studying the simple, predictable vibrations of the surrounding coastline. The waves and fury of the sea are encoded in the tremors of the shore. This concrete realization of holography suggests that our own universe, with its 3 spatial dimensions, might be a holographic projection from a vast, distant, and utterly foreign quantum surface we have yet to identify. A newborn universe might have been a place of perfect, instant connection. Quantum gravity paints this picture by starting with a mathematical object known as a complete graph. Imagine a social network where every single person in the world is directly connected to every other person, with no degrees of separation. In this primal state, every point is a neighbor to every other point. There is no such thing as distance, and the very concept of far away does not exist. This is a universe of pure, undifferentiated interaction, but such a state is unstable, possessing far too much energy. As this hot, connected network cools, it undergoes a phase transition, much like steam condensing into water or water freezing into ice. The countless links between nodes begin to freeze and break. Most of the connections vanish, leaving behind a sparse, structured network where only a few local links remain. From this cosmic freezing, the property of distance is born. 2 nodes that were once immediate neighbors are now separated by a long chain of intermediate points. What we perceive as a vast, 3-dimensional space is just this sparse graph of relationships. The speed of light itself emerges from this structure, as information can now only hop from one node to a neighboring node at a finite rate. In this model, particles like photons are not foreign objects traveling through the graph. They are defects or excitations within the frozen lattice itself. A photon of light is a vibration, a specific pattern of disturbance rippling through the network, its properties determined by the underlying geometry of the graph. The universe we see is a low-energy, frozen relic of a hot, deeply connected past, and every particle is a whisper from that age of perfect unity. Our final theory dares to suggest that the quantum world's deepest secret is a conversation between the future and the past. The transactional interpretation of quantum mechanics solves the mystery of the particle's definite path by introducing a breathtaking two-way street of causation. In this view, when an electron is emitted, it does not simply travel forward as a wave. It sends out what is called an offer wave, moving forward in time. But this wave is only half the story. The electron's eventual destination, the spot where it will be detected, responds by sending a confirmation wave backward through time. It is only when these two waves, one from the past and one from the future, meet and shake hands that a transaction is completed. A real particle is exchanged and the event we observe becomes definite. This handshake across time explains the infamous weirdness of quantum experiments without any spooky action, grounding it in a physical process where effects can reach backward to influence their own causes. Now, what could this possibly have to do with gravity? The connection lies in the profound non-locality of both phenomena. Gravity, as Einstein taught us, is the geometry of spacetime itself. Quantum transactions are inherently non-local, linking distant events in an instant. Some speculative ideas propose that these backward-in-time confirmation waves are not just abstract calculations. They create tiny, momentary distortions in the fabric of spacetime. Each quantum transaction, every single particle interaction in the universe, might generate an unimaginably small ripple in the geometry of the cosmos. Gravity would then not be a standalone force, but the statistical accumulation of countless quantum handshakes reaching across time. The curvature of space that holds planets in their orbits could be the large-scale echo of this constant, quiet negotiation between the past and the future. In this radical vision, the universe is not a collection of things, but a network of events, all linked by a dynamic and timeless dialogue. Perhaps gravity is the tangible memory of this cosmic conversation, the weight of all the possibilities that were and all the certainties that will be. 30 paths diverge in our quest for quantum gravity, from the silent music of strings to the frozen geometry of spin networks. We have wandered through landscapes where space is an emergent hologram, time is a fundamental flow, and gravity is a cosmic mirage born from quantum information. Each theory is a different lens, a unique language attempting to decipher the universe's deepest code, and not one has yet claimed the final victory. This astonishing diversity is not a sign of failure, but a testament to the profound mystery we are confronting. The ultimate answer, when it is finally found, will do more than just complete a textbook equation. It will shatter our most basic perceptions of reality, redefining what it means to exist in a cosmos where space, time, and matter are inextricably linked. The journey itself reveals the breathtaking creativity of the human mind, reaching for truths at the very edge of comprehension. So we turn this final question to you. Which of these 30 visions of reality resonates most deeply with your own intuition? Is our universe a symphony, a network, a computation, or a timeless shape? Share the theory that captures your imagination in the comments below. The conversation about our cosmic home is just beginning. The search for quantum gravity is moving from the blackboard to the laboratory. After decades of pure theory, scientists are now designing experiments that could finally give us a glimpse into the quantum structure of spacetime itself. The next generation of gravitational wave observatories will listen to the universe with unprecedented sensitivity. When black holes and neutron stars collide, they shake the very fabric of reality, sending ripples across the cosmos. Future detectors like the Laser Interferometer Space Antenna, or LISA, will be so precise they could hear the faint hum from the Big Bang itself, a primordial gravitational wave background that might carry the imprint of quantum gravity. Meanwhile, particle colliders continue to push the energy frontier, seeking any subtle deviation from the standard model that could hint at extra dimensions or the faint signature of a graviton. Some physicists even propose tabletop experiments using super-cold quantum systems to simulate the behavior of spacetime, creating analog universes in the lab. The path forward is a collaborative one where cosmologists, particle physicists, and quantum information scientists are all comparing notes. To follow this adventure, you do not need a PhD. You can watch live streams from major observatories, follow science communicators who break down new papers, and keep an eye on the social media feeds of leading research institutions. A new discovery could be announced tomorrow, one that forever changes our understanding of the cosmos. The greatest chapter in this story has not yet been written, and you are here to witness it unfold.